So this is basically about drone-based all-weather entanglement distribution. So we are aiming to do a drone network system which like has to endure all weather, right? Because we are supposed to be like doing it for military purposes and so on. So it's like drone-based all-weather entanglement distribution, and which means entanglement means that there's quantum elements inside this. So the aim of this paper is to create a free space quantum network. We know what a free space is, which means there's no fiber optic connections, nothing. It's just quantum stuff propagating in free space. And then the quantum satellite is actually a best bet because it overcomes the photon loss over large distances. But then there are challenges in this. What are the challenges? In real time, we need all location coverage, right? Because these photons can dissipate in different directions. And we also need to have multi-node construction. Multi-node is like basically you have some data. You have like n variables, so on. If there are n systems that want to access the same kind of data, I think most of it should go up. Yeah. Yeah, thank you.
Huh.
Yeah, cool. Yeah, yeah. So multi-node is when we have some data and then n devices have to access the same kind of data. So that is like a challenge when we have quantum satellites because of effects of superposition and all that. And then this is like it's complemented by the diversity of modern drones. Like different drones have different kind of protocols, right? So that is a problem here. And then in this paper, they aim to demonstrate the first drone-based entanglement distribution in all weather conditions. And then we have something called the Closure-Horn-Shimoni-Hole S parameter, which is like very important for quantum-based distribution systems because it is like the proof of the Bell theorem. We know what the Bell theorem is, right? Like different states cannot, the locality constraints and all of that. So here they basically, in the end, they like prove that their CHSH parameter is good. And that's how they implement the whole thing. And then here they first talk about satellites, and the disadvantages of satellites is that we need like on-site, like the line of sight communication, right? But we don't need that for drones. And so for that, to make it more efficient, they have symmetric beam apertures for both the transmitter and the receiver. And all this is in an localized area. And then so we can have like this can be put in drones that have plug and play local area coverage, or to high altitude drones for wide area coverage. You know how this works. We basically have a and then we have the base aerial drone. We establish communication between them and all. So they basically say that UAV is a much better option for quantum satellite. So the quantum network is the ultimate solution for secure data transferring, where any unknown quantum state cannot be copied or amplified. Why? Because we know that that's a constraint called no cloning theorem in quantum communication systems. But then the problem is that this nature, it sets a poor tolerance to photon loss in the network channels. I told you about that, like because of superposition effects and so on, we have photon loss in the connection channels. And then this limits the communication distance and the data rate, how much data is being transferred in every per unit time. So the solution to this is to have a free space quantum network, because in free space quantum network, we don't need much of hardware. We just have to like optimize all the channels we have through single mode transfer and so on, and just optimize all of that to get a proper thing. So the difference between this and our system is that we don't plan to use entanglement because we are not we're optimizing for a wide area coverage, but this is just another approach to a drone-based satellite system through entanglement distributions. That's why we plan to use BB84 and B92 and so on, right? But here they use entanglement distributions. So what are the problems with quantum satellites here? They talk about how low orbital satellites, they only establish quantum data link for certain ground locations with a limited time window. So all of this, they basically say that UAV is a much better option than having quantum satellites, though quantum satellites offer better data in and output speeds. So UAV, The drones can be used to establish communication on demand and multi-mode. I told what multi-mode was for real-time coverage in different space and time scales. So they have like the advantages with mode is that they can go to like even 25 to like they can have like kilometers of altitude, and they can have flight time for 25 to 30 days, which is can be improved with modern communication systems also. So here, by connecting such portable quantum drones with exit satellites and ground-based nodes, a quantum network with full and broad coverage can be established. And can you scroll down, please? That's a picture below.
This or
yeah.
Oh man.
Yeah, this one. Yeah, the first one. Yeah. So yeah, we can see that, right? So we don't need to have like such a big wide area coverage, but these people are talking about satellites and on that scale, right? So they take into account the Earth's curvature, and they have linking distance of hundreds of kilometers, and that's why they use entanglement. Why we don't necessarily have to use entanglement is because we have a smaller area of coverage. Within these people aim to have linking distances, as you can see in the graph, of hundreds of kilometers. So that's why they use entanglement. And then that's why they have to like synchronize their beam apertures also. They have to be symmetric so that we don't have dissipation effects and all. Like in the first paper, we had the photon incident beam splitter thing, right? Here it is the same thing almost, but for satellites. Mrs. Can you scroll down, please? Yeah, thanks. Yeah. So in a drone-based network, we don't have beam diffraction from like satellite to ground. That's what I talked about before. And multi-nodes can be applied to divide a long link into shorter links, because we can always have like different key distribution systems different key distribution systems, different devices connected in the same network, right? But a satellite is pretty expensive to establish, and that's why drones are much better. So there's something important called a single mode fiber technology here, which they don't like use it in between the satellites, but then they use it in the ground-based system, which communicates to the aerial drones. It is like there's only one optical mode which can travel to that single mode fiber, and this is a symmetric and we have symmetric transmitter and receiver beam apertures. This basically serves to have a synchronized communication across all the devices. And here, here we have like 2.79 decibel loss can be achieved for a 100-kilometer link. So this is pretty good, right? We just have a 2.79 decibel loss for a 100-kilometer link. And this is for only like a 300-millimeter beam aperture. And then, so here I talked about the CHSH parameter before, which establishes the Bell's inequality. And here they have a pretty good thing of 2.49 plus. So apparently, like till 7, it is like a good CHSH parameter. And here they have like, so the lower, the better. So this is like a good thing. So because they have all of these beam apertures and single mode fibers and so on, this drone communication system can be established in all weather operations, because it's just light that's traveling, right? Even though there's day or night, because we are having quantum effects involved in all that, can be done in all weather conditions. And then 12 decibel node-to-node losses achieved with high precision. They have something called an AET system here, which is nothing but an acquiring, pointing, and tracking system, which is that it basically tracks the position of all the drones in the system, and then they like calculate the noise rates, and then the key is established, and then the communication starts. And then the weight of our drones are kind of like light, but then here they have a 35 kg takeoff weight, and they have large beam apertures. So this can be like adapted to high altitude UAVs with like almost the same ratio. And then we can have a multi-nodes network, which I talked about before. And then this obviously guarantees a broad area coverage. So here they use like half wave. So the whole thing here is based on the polarization ability of the half-wave plate, all the beads that are involved, and they use a half-wave plate HWP2 and a quarter-wave plate QWP. They're tuned at different places to correct angles. And the maximum polarization in entangled photon state can be expressed by the psi is equal to HV. So the H of V here, it represents the horizontal vertical polarization state, and 1, 2, they denote the output ports connecting to the Alice and Bob links respectively. We know what the Alice and Bob links are. Yeah. So before they start the communication, yeah.
Good.
Yeah. So before they start the communication, they basically do all correlation measurements to see if everything is like separate and for their own right. They have like HV, the 0 state, and the HV, the 1 state. And then they have the HV 1 plus root 2, 1 plus 0 by root 2. And then they have the 0 plus 1 root 2, the usual quantum computer thing we do. So they basically do the correlation measurements to see if to make sure that there's no relation between any communication thing established. And then they use the SMF coupling technology. It greatly enhances the signal to noise ratio for all weather operation, because there's just one mode of light that is traveling to the fiber, right? So which basically isolates all the communications that are being established. So they for tracking precision, I talked about APT before, which is acquiring, pointing, and tracking that system, and they use it bidirectionally because the ground station has to communicate with that on top, and that's the checking that goes on between both of them. And then each of these APT units is composed of a telescope platform. So here they talk about optimizing from satellite stuff to the drone stuff, right? So this is like just hypothetical. And then they have like 3 axes together, and they have something called a gimbal stage. A gimbal stage is nothing but a stage where we mount optical instruments. And here, because the whole system is based on optical precision, optical polarization and all of that, they use gimbal stage. Before the so we know that when entanglement comes in, we always have a classical system and a quantum system, right? Here, before the quantum measurement is done, they have a classical test of the
No. Continue. QMLT.
I'll continue.
Yeah.
Yeah. I think he's for the other meeting, the QML meeting.
Yeah. Put him into the.
So, all right. Yeah. So before the quantum measurement, a classical test is done of our APT system at the link distance of 100 meters. So I showed the first image before, right? They have like scales on the link distances in hundreds of meters. So that's like a test link of 100 meters. Let's just scroll down, please. Yeah. Thank you. Yeah. So here they basically illustrate how the system is basically done. The schematic diagram of the APT system and its performance. You can see that they have coaxial cable and all that, and it generates the feedback system to the gimbal image. It's just how they say that we can use this optical protocol to establish quantum communication. I don't think this is very important for us here because we are going to do using QKD and all that, but this is how it is done in the paper. They show the noise ratio and how the SMF like reduces the noise ratio and all of that. Then we have the entanglement system. Just could you please scroll up? Could you please scroll up? I think this is like the next figure.
This one, right?
Yeah. Thank you. Yeah. So then we have like the entanglement system, right?
Continuous.
Yeah. So then we have the entanglement system, which is like the core of this whole protocol. And the AEPs and the TXAPT are just fancy names of every encryption system they have in that. And they have the polarization connections correction system at in real time to maintain original entanglement state from the source against air vibrations from air turbulence. So this like accounts for air turbulence and the entanglement itself. So that's why they call this an all-weather system. And this is, we know what this is. This is this is like the modified version of Bell's inequality. And then A, B, and A dash and B dash here are projection angles by which the polarization is done, how the telescopes are placed and all of that. Meanwhile, there's a classical communication link, which is utilized for a coincident count synchronization. Coincident count synchronization is that we don't want like different signals incidenting from the the transmitter and the receiver, right? So they maintain a count of every communication signal generated here from that, even though to like account for the noise and all of that. So here this is done like classically. They use optical fibers for that, the SNF I talked about. So that's the end of the paper. Could you please scroll down? Yeah, thanks. So this is the scheme and the measurement results of the experiment. They have all of these communication systems. We have Alice here and we have Bob here, and there's a quantum drone node in between them. And then Alice has certain communication stuff. She has a set of polarizers and he has a set of polarizers. And then we have a classical communication system that has a fiber connecting them. So this is like I talked before, they maintain the Bell states and they do all of that, and that's how they do. So the conclusion here is that if we want a drone-based communication system for a big area, like for kilometers, so on, the kilometers and all, we need entanglement systems to survive all weather conditions. And then this is sufficient for, like, that's what they say here. This is sufficient for the realization of a drone-based local area quantum network within 40 minutes of on-demand coverage. And then we can like obviously customize our components and maximize the local area with specially designed drones. And then the link distance, even if it's done that way, this is like a relatively old paper. I think this was done in 2013 or something. And so the link distance, even then with this protocol, they could have link distances of 300 kilometers. So with present technology now, we can optimize our link distance to even hundreds of kilometers and have more time of coverage using this kind of protocol. Yeah, Moses, I actually said the conclusion part as well. That's what it said. So.
Oh shit. It's completely on mute. Wait, I was on mute. Like for how long? Did you guys
Probably a couple minutes.
couple of minutes? Okay. All right. So I was just saying, oh man, God damn it. I was saying, as far as schedule is concerned, from April second week onwards, we'll get into the actual implementation. So this also for Maima and Achit who will be watching this. And Nilay, you were not aware of that, right? So we'll start implementation from April second week.
Yeah, like I was actually busy, like really lost with the lab work, so I couldn't catch up.
Super cool.
Yeah, like this paper which Bhuvaneshi presented, that was linked with the transmission of data, right?
Ah.
Okay. And I guess the link why it's all weather and an entanglement, the logic is like suppose if the weather conditions are not well, so if I know my state, I can predict the other person's state.
Ah. Yeah, sounds like that.
Yeah, like if my state is 0, so I'm pretty sure the other one should be 1.
Mm. But weather is like a continuous series, right? It's not like 0 or 1. So how do we do that then?
Yeah, exactly that.
Mm, the link distance can exceed 300 kilometers within the Earth curvature limit and with reasonable aperture sizes, which can further cascade it for larger scales. Hmm. Okay. Chalo, we'll meet tomorrow at
Yeah,
9.
yeah, yeah,
But the
yeah,
videos are put up in the team page, okay? You have a look at it.
sure, yeah.
Ah, right.
Yeah, Sam, yeah, like, are you aware about the unitary fund?
Yeah. People have been telling me about it. Yeah.
So like since like we were actually trying to get on to the real working of it.
Ah,
So like if you could just write a proposal and then appraise them because that takes a time, I guess.
yeah. True.
That would be like much more like later on when we approach some people, like when we have the backend pending,
Hmm.
that I guess it could be a good thing.
Yeah. How much are they investing?
They gave up like $4K.
Hmm.
Like that's like in 2 batches, I guess. And initially we need to they gave like 1,500 or 2,000. Then later on with the progress,
Hmm.
you can take up the other one also.
Hmm.
Like people have got it like for just developing quantum communities. So
Huh?
like various people like I know they have got it like for just developing quantum communities all around the world. And like many eventually use it like for their extensive research purpose.
Hmm. All right. Um,
Uh,
stop it.